Hello everyone, I'm Shashwat Dhayade. I'm an undergraduate student majoring in data science with geoscience as my focus, and I will be starting my PhD soon in fall 2025. So today we're going to talk about fish and chemicals. Why am I mentioning these things? Because these chemicals are not only going into the fish, but going into our stomach because we eat these fishes, which poses environmental and public health risks. So in this study, we examined different chemical feature representations to classify fish bioconcentration mechanism, which just means how these chemicals interact with the fish. First, we obtained a dataset, a public dataset, which contained 763 chemicals with their chemical formula representation as smiles. Then we performed feature engineering to extract 5 new datasets. First was physicochemical features, which contains log BCF, which is how highly concentrated that chemical is in the organism, and log KOW, which means if it is more attracted towards lipid or the chemical is more attracted towards water. These two main important features are present in these set. Then we generated RDKit features. First one had 198 features. The second one, we add log BCF and log KOW to these RDKit features. We also create molecular fingerprints, ECFP and MACCS, which are represented in zeros and ones. Zero representing there are no structural feature or functional groups present. One meaning there are some structural features and functional groups present. Different molecular fingerprint like ECFP and MSCCS have different bit structures. That's why we are employing them. Then we used supervised machine learning algorithms on these datasets, gradient boost decision tree, random forest, support vector classifier, and logistic regression to predict mechanism classes. Class 1, which is inert chemicals, which only interacts with lipids. Class 2, which is highly toxic chemicals, which interacts with proteins and tissues. Third, less bioconcentrating chemicals, which are eliminated through metabolism. So it creates a classification problem for us. All models are run 25 times using 5-fold cross-validation and 5 repeats. All hyperparameters are fine-tuned using 70% training, 10% validation, and 20% test data. Now let's move on to results. Panel A, which is physical-chemical features, and Panel B, which is RDKit features, show models with comparable performances with GBDT performing with high model accuracy consistently. I think GBDT performs better or it has high model accuracy consistently because it follows a step-by-step learning process. It adds model to the previous learners based on the previous mistakes. Panel C, which is our main feature dataset, which contains RDKit, log KOW, and log BCF. This is our main dataset because we are going to create web tool out of it. Imagine if there was no web tool development. How are we going to get the bioconcentration class? Are you going to train these models for hours and hours and hours? Or are you just going to put the chemical ID number, log KOW, and get the class prediction in an instant? That's why. Then we use log KOW and log BCF because they're highly important features, as you can see in the feature importance plot. We can see GBDT performs a high with 0.863 accuracy and high recall because we don't want class 2 to be predicted as class 1 or class 3. That's why we consider recall as a good parameter metric over here. Molecular fingerprints are less competitive than physicochemical features because you can see the model accuracies are quite low. In conclusion, accurate prediction of bioconcentration mechanism is important for chemical risk assessment. Our GBDT model achieved high prediction performance for physicochemical features and RDKit generated features plus log KW and log BCF. Thus, these different future representations are important for our project.